All right. Hey, everyone. Welcome back to another week of OS Dev Gardening. Today, we are doing something kind of new. We will be looking at the JOS OS, JOS OS. Let me get my board up. Let me get get all set up. Yeah. Just getting my OBS and everything set up. But yeah, so far we've been using XV6, but I didn't really love it. The build system kind of wasn't good, and also it was kind of full already with functionality, and I kind of wanted to do a bit more of this work by myself, and so now I am switching over to this other one, which JOS OS MIT. Yeah, I'm just going to pull up literally the MIT labs. And I think I might just kind of work through some of these today, actually. Let me see, there's a few things I'm missing. I want to get my chat, my text set up. What should it say? JOS kernel intro. Feel free to say hi. Okay. That's I don't know where to put this text. Maybe I'll put it like up in the top here or something like that. Trying new things this week. Yeah, so the thing that's immediately cool about JOS is that it seems much more mature than XV6. I'm just going to go back to this thing. So one thing that kind of confused me actually is I was originally starting with XV6 for all of my OS development, and XV6 says that it borrows code from JOS, which made me think that JOS is older than XV6. And so I thought it was more like XV6 is more modern or something, and a better starting point. But then I have been learning that it's more complicated than that, maybe. I don't know. That JOS was actually used as late as 2018 for MIT's OS class, and immediately has like a different look even to like the repo. Like XV6 is just this one directory, which I know all too well by this point, and it's kind of disorganized. On the other hand, JOS is actually quite organized, and has a bunch of these directories already included. Need to trust this folder. Manage, trust. Okay, trusting. So yeah, JOS is already much more mature looking. It has like this kernel dir. It has the user dir, which actually doesn't have too much in it, which is actually a good thing, because I didn't really want to have a fully fleshed out user space like already necessarily. I kind of wanted to be able to build it up myself. The obj dir is actually the out of tree build directory where all the object files go, which is awesome. If you've been watching this stream, I spent like a stupid amount of time trying to implement this myself for XV6, and I got like a little bit of progress, but it was really not very fun for me, and I didn't even get that far really with it. And so they even implement this nice out of tree build thing where the directories inside mirror the source directories. There's this lib directory, which is pretty cool, which is routines that are shared between the kernel and user space, I believe, or at least things that don't really need to be in the kernel, like some easy string functions. Just checking the chat. Wizard, what's up? Great to have you back. Thanks a lot for tuning in. Yeah, I'm pretty excited for this one. today is our day where we're going to go through this like new OS and just kind of check it out, see if we want to use it more in the future, or even at least just learn about it a little bit. Yeah, for anyone else watching too, would love if you just said hi in the chat. Feel free. Feel free. It would be great. Very chill and casual here. Include, the inc is the include directory. Kind of interesting. They do it this way. Yeah. So anyway, the point is that this just feels much more mature. Frosty, thanks a lot for the comment. Can't have a nice stream, can't watch right now, but much love. Yo. Nice. Well, thanks a lot anyway for just checking in. Appreciate it. There's some different stuff here. Boot has its own stuff. So anyway, this seems just way better in my opinion. There's a lot of cruft that I don't actually care about for this grading stuff. So yeah, we'll probably get rid of that anyway. The makefile is named kind of this weird GNU makefile thing, but I have it running kind of so far. Yo, Marshall, what's up? What's up? Thanks for joining the chat. Let me show you what I got so far. So I just cloned the repo from the MIT website. And I'm starting with just the absolute basic instructions. And I was able to clone it from this, this like URL. Just real quick, they have a bunch of, this is a pretty useful website. There's all these tools and stuff like that. I was a little bit worried about the tool chain. Like the tool chain is always a bit, can be like very fiddly, or it's like, where do I even get a tool chain? But luckily I was actually able to just use the tool chain that I already have working from x86, which is this like, it's the i386 ELF tool chain that runs on Mac but produces 32-bit x86 binaries, and that was pretty easy to get set up. I think I just found that from like searching how to build xv6. So I'm still using my old tool chain, but it works. What am I doing here? Does the clean rule work, for example? Yeah. So I can run the clean rule. Just look at the makefile is also much better. The makefile seems a bit cleaner. I already mentioned that the build system is much better. I don't need all this junk about this stuff. But it seems to be handling this dependency stuff automatically. That was always such a pain. I was trying to do that in my old build system, and the one I was rewriting for xv6. But anyway, let's just take a look. What targets are available? Also, yeah, check it out. They also do this recursive make thing, which is cool. I don't want makefile tools. Or do I? Yeah, sure. Actually, sure. Why not? So they also do this recursive make thing, which means each of these directories gets its own makefile. And it's kind of like a makefile just for the directory, which is pretty nice. I don't really understand it yet. Maybe we can get more into that later. But I'm super happy to not have to do this stuff and have it kind of done for me. So yeah. Actually, this is kind of, yeah. So I don't really understand how this works, but it doesn't actually seem that different from what I was doing last time. Or I'm not going to pull it up, but anyway. So this is all good news. But what targets do we have to build if we wanted to? Okay. So this is the one that I was interested in. So the QEMU target goes all the way, builds the kernel, runs it in QEMU. I think I got that working too. So I just run the QEMU, and then I'm not really sure what this is. Also, I think, do we have a console? Yeah. So we also have like a console here. So I don't really know what this is. We will figure this out as we go through it. But what's immediately different from xv6 is that this is not like a user space shell. This is some kind of low-level kernel monitor. With xv6, you at least the version that I was using, you build it and boot it, and it boots all the way through the kernel and all the way even into user space, even into a shell that's already running in user space, which is pretty cool. But that means that a lot of work already exists to be even able to get this far. And so this thing stops way earlier. I don't even know what's happening, but I don't think it's very far along at all in terms of like kind of getting to user space. I think we have a very long journey to go. So that's a one very obvious difference. So I will just quit that. But I just want to kind of get to know this build system a little bit better because we have this QEMU target, but that takes us very far and even executes QEMU. There's this images variable, which I failed to find. Okay. Warn object kernel. What I'm looking for is I just wanted like a simple way to just build the kernel, but not run it. I actually don't really see that. Also I don't know what this warn thing is. I wonder if there's something I can find here. Also, why is there an all target in the kernel fragment? Do all of them have this? I wonder. Actually, are there even other make frag? There's boot and kern. Boot has a make frag. Does this have an all rule too? No, it doesn't. So I think actually, yeah. So if I just if I start off with like a clean setup and I do, I only do that. That's what I was looking for. That triggers the all rule, which is actually inside the kernel make file fragment, which triggers this thing. Oops. Which specifically tells it to build the kernel.img. And I wonder how similar this is going to be to xv6. Well, I think it'll be a lot simpler because there's a lot less. Like a lot of the complexity with xv6 was because it already had like this user space initialization code like blob thing that it was like linking in and trying to use and stuff, and that was kind of complex. This boot stuff seems simpler. Overall seems a lot simpler just because there's a lot less here. Like xv6 had a lot of complexity. There was like the mode where you build it where it uses like a disk, but then there's also this like in-memory disk option that I was never sure about. So anyway, that's just kind of getting like our feet a little bit wet into what this is all about. Grub, interesting. Yeah, so anyway, that's kind of that's just kind of where things are now. So let's just so here's what I want to do in general. I think I want to take a brief tour of just what's around, and then we'll start off with some of these assignments and see if I can like do them or how much I fail at them or whatever. So let's just take a brief tour at what we have here. So starting off with boot, we have our boot assembly. So this is our typical stuff. Ultimately, I think we're doing the same kind of thing where we are assuming like a old school IBM PC type of setup, like 32-bit x86, where the first like 512 bytes are loaded for the boot process. And so this is all that early boot stuff, the A20 line. This is not the kernel. This is just the boot, like a small bootloader. Then we have some basic assembly to get even just the bootloader going. And then it goes into the bootloader's main. It's a dirt simple bootloader whose sole job is to boot an ELF kernel image from the first IDE hard disk. Nice. Okay. So there's some details about this. The bootloader is stored in the first sector, so the first 512 bytes. Second sector onwards is the kernel, which is an ELF file. So this boot loader is going to have an ELF loader probably in it. Okay, I mean this is super nice. It tells us what's happening. Yeah, yeah, this is a pretty nice comment to have. And yeah, I don't feel too overwhelmed just yet. But yeah, so now once the boot assembly of the bootloader finished, it triggers the C part of the bootloader, which actually implements the ELF, the kernel, like the loader. And it's actually interesting how simple it is. So they must have some driver or something, some basic, yeah. I mean, this is the driver. It's the basic IDE, which is the disk, I don't know, the disk protocol or something, which I don't really know. We can probably look up exactly what's happening here, but it's using the special I/O instructions to interface with the disk. Apparently you need to spin on some stuff, and then you can send some commands like where you want to read from. And I guess it reads a whole sector. Yeah, 512 bytes. So what is this? In SL. x86.h. Yeah, no idea what that is. I'm not familiar with the... Oh, so it's part of these in and out instructions. So these functions are just wrappers over the assembly out instruction for, I think, like 1 byte of data, which is how you like communicate with the device. Apparently there's some well-defined port numbers, or like, yeah, some well-defined numbers for where the device lives in physical memory. I'm not sure how like that's defined or how that's declared or how you would know to write the code this way. Then I don't, yeah, I mean, yeah, what is a CLD instruction? Clear the DF line. Okay, it's pretty esoteric. I don't know what the direction flag is. It's kind of, well, okay. Direction flag is used to influence the direction in which string instructions offset. So it's part of using the whole rep instructions thing. These other things. Okay, that's like kind of detailed. I don't know if I care that much, but that's just a way to read a string, so to speak, into memory. Okay. Anyway, the ELF loader is pretty simple though. It reads 8 sectors off of the disk. And that's just hard-coded, I think, if I understand this correctly. What is this? Count points at offset from kernel into physical address might copy more than asked. That's kind of weird. Okay. Into physical address. Interesting. Elf. Header. So one thing that's also interesting here is that somehow we are just assuming that this physical address is free. And I think that's actually related to this thing in the make file. How many, or maybe not, I don't know. How many zeros is that? That's like 7 zeros. So is this, does this match? No, it doesn't match at all. So that's a mystery to me still. But then it somehow knows that that place is free or something, and there's a lot of free space, and offset count. Okay, but really all it takes to load an elf is to iterate through the program headers and do what they say, basically. And they basically just tell you interesting. The load address as well as the physical address. We can look into that in some more detail later, but those are just some basics. Okay, so we have our bootloader, which loads the kernel. And we have the kernel itself. What do we have in here? We have console. We have a console driver. Text mode, interesting. I think the console driver. Oh, I think that's what controls like that screen that Kimu made. Oops. Okay. Okay, whatever. Console driver. We have our kernel entry point, which is interesting. Oh, I just realized I'm not sure I'm running my my palm tree break thing. Okay, just in case. Yep. So there's some esoteric stuff about the boot process. Physical address of the entry point. Okay. Okay, this is like quite detailed stuff. I would be interested to learn more about it, but I'm going to skim it for now. Load the physical address. So basically, the first thing it does, it sets up virtual memory in a very basic way. So there's no virtual memory support at all. Yet the processor is not running in paging mode. So we set up a trivial page directory that translates virtual addresses to physical addresses. Okay, the C code is linked to be using some like addresses or something. Where, just, yeah, out of curiosity, where is kern base defined mem layout? Okay, so the kernel is like linked to like operate in this way. However, so it seems like the kernel has been actually just copied into the lowest like part of physical memory though, if I'm reading this right. Okay, in lab 2, which I'm going to try to do maybe. Load the physical address. Entry page dir into CR3. Entry page dir. Okay. This is called higher half kernel if you want to look it up. Okay, cool. Thank you. Higher half kernel. I've not heard of that before, actually. Thanks. Oh, wait. Maybe I know what you mean. So, if you're talking about where the kernel... so I'm aware that the kernel often gets mapped into virtual memory in like the highest like part of virtual memory, like on 32-bit in the highest gigabyte, for example. Yeah, so yeah, maybe this is related to that, although, yeah. Anyway, locate the physical address of entry page into CR3. So this is interesting. I mean, this is very fundamental, just like stuff, like, so where, so we have this like compile time, constructed page directory. Page directories and page tables. Let's start on a page boundary, hence the aligned attribute. Okay. Interesting. Oh, you cannot, because restrictions on linking and static initializers use X plus rather than ORing. Apparently you cannot use ORing in this like context where it's like a global variable that you are like initializing somehow, but you can use a plus operator somehow. That's kind of interesting. Yeah. Somehow, okay, so we have like this variable and we can access its address, but we need to do this relocation thing to actually determine the physical address, which I believe is what happens here. It's like a macro that just subtracts the current base offset. I think I understand that. Maps a symbol from its link address to its actual location in physical memory. I think I'm getting it. I think I understand. So that if I'm understanding this correctly, the actual kernel elf is loaded at physical address 0, which I guess, yeah, sure, why not? To verify that, oh wait, I think, yeah, and to verify that, we would look at the bootloader. And I actually think that kind of explains something. I was a little bit confused. No, maybe I'm wrong. Read first page off of disk. Into physical address PA. Okay, so I think maybe I don't get something. Offset 0 PA. Okay, I think, yeah, there's like something I don't quite understand where, why is, this would make it appear, oh wait, no, wait, so, okay, so we load the kernel from the disk into like this kind of random place that's like kind of like high in memory a little bit-ish. And then, but that's not where the kernel is going to be like low, like that's not the final place where the kernel is going to run from. That's just some scratch space to like hold the kernel so we can operate on it. Because before this, it was on the disk. So we need to take the kernel, put it almost literally anywhere in memory, I think, and then we just need to know where that is, and then we actually load the kernel. We interpret the program headers and do these commands, which I kind of glossed over before. So, okay, that's a little bit becoming clearer. And then my guess is that something, I mean, also there's probably comments that kind of just tell all the answers to the things I'm wondering about. But I am kind of trying to figure it out for myself without reading them a little bit. My kind of guess is that the way the kernel is, like the elf file of the kernel would somehow tell the loader to like put those pages near 0, because that's what would kind of make sense. That's how the pages would end up sitting so low in memory, maybe. But anyway, so load the physical address of entry point into CR3, entry page dir. We enable the page directory, this like really simple one, and then activate paging. So now, if I understand it correctly, now from this point on, we are running with like a very basic virtual memory enabled. I think Arash in the Discord warned me about this. It's using AT&T syntax, which I kind of don't know how to read. Or like, I'm always so used to reading Intel syntax. AT&T syntax, like things flow from left to right, which is why it's like EAX, move this thing into EAX, move this thing into CR3, move CR3. Oh, I see. To enable paging, you need to like flip some bits in CR0. So we move that into EAX. We do some mutations on EAX or in some of these bit flags or whatever to enable like all this stuff. And then we put that back into CR0. And just like it says now, paging is enabled, but we're still running at a low EIP. Why is this okay? Jump up above kern base. Quick, reading the comments. Yep, the kernel is physically located at 0. 1 megabyte generate, that's what's written inside the elf headers, but the kernel code is linked at a higher address, hex C0000. That means we need to fill stub page directory, or else the very first instruction run after activating paging will cause a page fault. Right, okay. When you say generally, like you're drawing on some experience there, like is that some practice for other OSs you've worked on? And so you're saying that in this case, it happens to be at 0. In generally, it's like for other OSs, it's at 1 megabyte in physical memory, but for here, it happens to be at 0 for some reason. Is that what you're saying? Okay. Yes, exactly. Okay, cool. But this means we need to fill the stub page directory. And I think I understand what you're saying here. So you're referring to this like really kind of initial page directory. which has exactly like 2 entries. It has the first entry, I believe. Yeah, I mean, it's commented. So it's literally just 2 entries with 2 mappings. So the first mapping is for that actual 0 part. Interesting. Okay, so this is basically an identity mapping, if I understand it. It's mapping virtual addresses 0 and 4 megabytes to physical addresses 0 to 4 megabytes, just so we can continue to access all that stuff we put in that low region. I have a very little experiment I want to try here. So now if I have readelf, I can, having it linked to hex C means you can reserve 1/4 of the virtual address space for your kernel's code when dealing with programs user space. Interesting. Okay, yeah, I don't have all these like hex numbers like super memorized. And I'm also kind of like needing to adjust the fact that we're on 32-bit and not 64-bit. Right. So I guess hex C, but okay, interesting. Yeah. So the test I wanted to do is, so we have a kernel, and we can take a look at the program headers. Right, okay, yeah. This is interesting. There's only one program header. And is it so? I'm not like immediately understanding it. So this physical address thing is the same as what we saw here. It's like, what is it? 4 zeros? No, it's not even the same. But again, this is totally irrelevant. Yeah, that was kind of a nonsense comment. But read segment. What I actually find kind of interesting. Wait a sec. Saying, so the first argument is the destination. It's offset from kernel into physical address PA. Okay, that's like the destination. All right, thanks, Lizard. See you. Count is how much to actually read count bytes at offset from kernel. At offset from kernel. So does it hard code? Like, what is offset from kernel? How is offset used? Kernel starts at sector 1. So it kind of like rounds it into sectors, maybe. But then does it touch the disk again? We can use physical addresses directly. This won't be the case once JOS enables the MMU. So that's a little bit funny to me that it's like touching. Is it really touching the disk again? Oh, but wait a sec. Wait a sec. Maybe, yeah. Okay, maybe I was a little bit misunderstanding this. I kind of assumed it was reading the entire kernel off of disk into the scratch space and then loading like from there. But I think I'm wrong. I think it is only, I mean, as the name would suggest, only loading the header. But if that's the case, why is this so large? Like, why is it necessary to load? Maybe, like, yeah. Like, how big is the elf header? Like, not that big. It should probably fit into one sector. I mean, let me know if I'm wrong, but like 512 bytes? I don't know. I mean, we could check, but we load the elf header. We load a bunch of stuff into this area, and then for some reason the elf loading hits the disk again, which is a little bit confusing to me. But maybe I'm just misunderstanding something. But anyway, in its writing, okay, so we get for each elf header, we then do this read thing, and we're using the data from there. And so let's just kind of take a look. So we have these program headers, and the PPA physical address is going to be this thing. Yeah, I feel like I could improve my, like, I just don't know these hex numbers super well. So 5, 1, 2, 3, 4. So how many like megabytes is that? So that's 1 megabyte. Okay, good to know. So at the 1 megabyte mark, which is exactly what Dali run, or however you say your username, that's what you're kind of saying, the 1 megabyte generally. So maybe I'm being like slow or something, but I'm still not understanding this connection between this 1 megabyte mark and like all this mentioning of like literally 0 in memory. But 20-second break. Right, okay, so good to know. So 5 zeros is 1 megabyte in memory. This is like a pretty high virtual address. Is that actually mentioned here? Oh, I got too many things going on. Main does. No. I want. Okay, entry.s is where we were still. And where is that mem layout? Maybe I should just read this file. Oops. Okay. So this is the virtual memory map. Okay, so this is all physically mapped at this address. So to continue my learning of this stuff, what does this correspond to? That's 308.40 megabytes. Okay. Interesting number. I'm just trying to work out. Yeah, we're in a 32-bit address space, so that's 4 gigabytes. What is 1 gigabyte again? Oops. Whoa. Hex. That's 440 with, so the high byte is 40 for 1 gigabyte. And we're at F0. Okay. Okay, I mean, that is kind of obvious, because if it's, yeah. If there's 4 gigabytes, then yeah. If there's 16, no. Yeah, if there's 4 gigabytes, then yeah, we work our way up from, 48C up, probably. Okay. Okay. So all physical memory mapped at this address. I don't get this diagram still, really. So that's the 4 gigabyte mark. We have this region, or physical memory exists, kern base case stack top. And so you can access what, like, okay, so in our case specifically, it's like hex F for some reason. Yeah. You were like, you've seen it with hex C or something before. I feel like I need to just understand this, like, the sense of scale here, though. So, because this hex F thing is not even that close. It's like so like 1 gigabyte is 40, so it's quite a bit. So we're not even close. Like, we're still like way early in memory, basically. Yeah. Something. Yeah. Right, so we just choose this place, hex FF. It's kind of like a, so we have basically this many megabytes. This is just such a weird number to me somehow, it seems. But wait, I feel like I'm messing something up here. No, I feel like I'm messing something up here. Like, this is pretty embarrassing. This is like, so how many, yeah, there's one, right? It's like, how, like, this is 1 kilobyte. Like, how many, yeah. 1 kilobyte, 1 megabyte, 1 gigabyte. So 1 gigabyte is 1,000 megabytes, basically. Oh, wait, no, okay, wait a sec. So yeah, this is like, right, this is the gigabyte range. It's like a 4 here. This thing is past, it's like bigger than this. Okay, caveman brain activating. Yeah, like, man, I feel like, yeah, caveman brain activating. Okay, like, what are all these? I'm super, I don't have a lot of experience with like just like reasoning with these like high hex numbers and stuff. So this is an address we chose. This is the 1 gigabyte mark. This number is smaller than that number, which means this thing is like very high in memory. Like, yeah, it's probably like, you know, now that my caveman brain is kind of like getting there. So now that's the 2 gigabyte mark, you know, that's the 3 gigabyte mark. And lastly, 4 gigabytes is like even higher. That's a 1, and there's going to be 4 basically like octets or whatever. Okay. Whew, okay. Now that I'm a bit anchored in my sense of like what all these numbers are, I can actually kind of intuit these numbers a little bit better. So this is like a high number. And I think I'm finally getting it now. That's 1 megabyte below the top of memory, right? Minus. So that's, yeah, minus. Oh, what the? Oops. Okay. So 4 gigabytes minus 1 megabyte is the C thing. That's what you were saying. And so, wait, no, I did this wrong. I did this wrong. Okay, now, yeah, so that's I accidentally did 1 gigabyte from the top. I actually wanted 1 megabyte. And if I am right, okay, what did the... Okay, wait, no, that makes sense because this 1 megabyte is only 5 zeros, right? So that's 1 megabyte. Basically, the question I have is like, how far away? Yeah, the actual question I should just be like doing is like, if that's 4 gigabytes, and this is like where we somehow happen to be, how much? It doesn't really even matter. That's like some number. And I want to know how many megabytes that is. 256 megabytes. Okay. I feel like I want to diagram this or something, at least to help my own understanding. Yeah, man, this is kind of a rough stream. I feel like I'm super slow with this, but so we have our we have like memory, right? Wow, okay. 4 gigabytes. 0 gigabytes. 1, 2. So I kind of did this wrong. Okay, 2 is in the middle. Duh. Okay, something like this. Yeah. 1 is like hex 4, basically the 40 in the top thing. 2 is 80. Hex C0. 4 gigabytes, hex 100. Okay, caveman brain is finally getting a grasp of this, of numbers. And for the record, 1 megabyte equals, right, 5 zeros. I'm just going to do this to make it clear. 100,000 hex, 1 megabyte. And for whatever reason, we're using I guess I feel a little bit weird about dividing it like this. Is that even right? 1, 2, 3. I think that's right. Yeah. So F0 million. For reference, each 10 bits corresponds to a new unit. Multiply by the remainder. 2 to the 10. Thank you. I did not actually know this. 20 to the 30 is 1 gigabyte, and then multiply by the remainder. 32 bits, 2 to the 2. Right. Cool. Thanks for the tip. Okay, so like this thing, this hex F thing is actually kind of high. It's like up here approximately. And I don't want an arrow. Ooh, the line's still there. And this distance is 256 megabytes. I believe, if I'm not like stupid and did this right, but I think I did this right. So 4 gigabytes minus the F address is this thing, which is 256 megabytes. Okay. Going back to this thing. Right, this is like actually quite high up in memory. I think I was totally wrong before. I thought I said it was like low or something. This is actually very high in memory. Such that there's only 256 megabytes left. And the actual massive gap maybe is like actually here. This is the, you know, I believe, but like, yeah, I'm pretty sure I'm correct with that. So this is actually this like massive, like, so this thing, like 1, 2, 3. So using my new knowledge of like numbers, I can now see that this is now the 8 megabyte mark because, what was it? Yeah. 1 megabyte is 5 zeros. That says 8. So that's the 8 megabyte mark. So then we have this like multi-gigabyte span from like the real bottom up to like the almost basically the top of memory. Okay. And this is just the virtual memory map, though. This is not the physical memory map, which is why like there's nothing here. Current base. Interesting. So there's some kernel stack, okay. So this is actually, I mean, what the diagram we're seeing here is like a very complete exception stack. It's like, yeah, it's very complete. And so far I haven't even gotten to any of this stuff, basically. I don't even know what produces this final memory map, or if it's even implemented, but it's going to be some like more complicated set of page tables, like obviously, especially this memory mapped IO one. There's going to be some page table mapping that maps this region to whatever physical memory region exists, which has all the memory like all the devices that are mapped into memory. Okay, cool. Yeah, it took me kind of a long time to understand that, but now I feel a lot more comfortable with just like what is going on, at least a little bit. Now that I have some points of reference of like what these numbers are, where they exist, like relative, in our whole space of of like memory that we have to deal with. And that is just helpful. And so now, crucially, I can finally kind of intuit these numbers a little bit better. So this virtual address is the same thing as the physical address. They both have the 1 megabyte thing, but this just happens to be like super high in our like hex/FO range or whatever. I don't actually totally get the significance of that at the moment, but offsets. Yeah. Okay. Anyway, let's continue exploring some of this code. I'm having a good time. This is kind of exactly what I wanted, actually, because I've always felt really unsure about all this stuff, and kind of just getting the sense of like all these hex numbers and whether they correspond to 1 megabyte or 1 gigabyte or whatever. So quick recap. So we have this. So I would be interested to see the physical memory map though, or like what that looks like, because we haven't. There's no diagram that I've seen so far. Also, that's kind of this is a mystery to me why it's so big, why it's reading so much data off of disk. Then coming back here to the original thing, I was kind of curious about. I wonder if I can understand this mystery. The mystery is all this code and comments talking about 0, physical address 0. There's all this stuff talking about physical address 0, which led me to believe that the kernel gets loaded from disk and written to physical memory 0. Okay, 20-second break. Be right back. Okay, quickly checking on my stream quality to make sure nothing is messing up. But yeah, oops. The mystery. Yeah, I'm just gonna try to figure this out and see if I can understand it. So I was led to believe from this thing that. Maybe I should just read the comments too. That the kernel is at physical 0. Physical address the bootloader loaded the kernel at. Usually the bootloader passes a map of physical memory to the kernel's code, which uses it to initialize the memory allocator. You might be able to have a dump function that if you're curious. Oh, that's cool. I didn't know that either. Appreciate that. Yeah. So I don't know how to say your name, but Dolly Run. It sounds like you have a lot of experience with this stuff, actually, which is super cool. Do you work in operating systems, or do you have your own hobby OS that you work on? I would love to hear about that. Okay. But for the moment, I'm just going to keep focusing on this thing. So running from the physical address, the bootloader loaded the kernel at daily run. Okay, weird. 1 megabyte. So let me see if I can even understand this sentence. The bootloader loaded the kernel at 1 megabyte. The code that loads that corresponds to the sentence is this code. This 1 megabyte thing should appear here in the physical address, which is the destination, and that is exactly what we see. That is exactly what we observe. Okay. The physical address load in the load head, like in the program header, the load program header, the only one, advertises 1 megabyte as the physical address, which makes sense. So that would lead me to believe that the kernel is copied from disk at 1 megabyte. So I'm still confused about this 0, but we'll probably get to that point. However, the C code is linked to run at kernel base, blah, 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 blah. Which means the point of this sentence is that we have this like whole kernel we built into like an ELF file, but we can't run it yet because all of that code is compiled to assume these very high addresses, I believe. Plus 1 megabyte. Kern base plus 1 megabyte. Kern base is that high thing plus 1 megabyte. So I don't like immediately. This is also the physical, the virtual map, so it kind of doesn't matter. But I think what's kind of missing from this diagram is where the kernel pages actually are. Like, where is the kernel's code? Can't, like, that's probably the user space program. Yes, I'd like to work with kernels later. I've tried developing my own lately, so I ran into the same questions. Okay, awesome. Very cool. Feel free to post a link to your OS if you released it publicly. I would be very interested to check that out. That's kind of my goal would be to eventually be able to work on this, but I'm obviously not there yet. But what I'm kind of understanding, or I guess inferring, is that up in this region, in this 256 megabyte region, that's like where the kernel code is at, like, yeah. And that's not shown in this diagram, but the kernel, yeah. But that's what we saw here. It's 1 megabyte into the kern base region. Right. C code is linked to run at this thing, which is exactly what we see here. Hence, it's called remapped physical memory. Okay, cool. Hence, we set up a trivial page directory that translates virtual addresses, kern base to kern base plus 4 megabytes to physical addresses 0 to 4. But why? Oh, but wait a sec. Okay, that kind of makes sense. There is this, for some reason, there is this 1 megabyte offset. Yeah, that's it. So if we're, let's like map it out maybe. I'm going to zoom in. I'm going to, yeah, I don't know how to do this. Okay, I'm just going to draw, like, this is going to be a whack diagram. That line is way too thick. Okay. Okay, so pretend, so that's not even right. Yeah, okay, this diagram I made is like too zoomed out because we're really focused on this like tiny region right here. So I'm going to make a new rectangle to help me understand this. And I'll make it a different color for fun. Can I align this with the other one? Okay. So in this case, now we're here and here. So I'm going to draw a line, oops, from here across. Why can't I make it flat? Okay, like I cannot make it flat for some reason. And I'll make an arrow that goes from here to here. Okay. And so we have this. We have our current base region, which is the top 256 megabytes of the address space. And this is not even going to be like really to scale. This is going to be super non to scale, but we have our 1 megabyte mark above this line. And then this is totally not to scale, but what we have 1 megabyte above that line, that's where yeah, the kernel is like linked. So the kernel, something about the kernel is like there or whatever. Yeah, this might be like kind of wrong, but I think it is roughly like maybe kind of right, where the kernel expects to be off like 1 megabyte or so from there. Plus a few bytes, okay. The bootloader loaded the kernel literally at 1 megabyte. Okay, so yeah, this is like totally not, this is like absurdly not to scale, but roughly speaking, in physical memory, the kernel's like down here. Okay, we have like our 0 and we have our 1, right? Okay. 1 megabyte. The bootloader loads things from disk, and it like followed the program headers. Kernel ends up here. But the kernel kind of expects to be up here. And so I understand it now. So just because there's a 0 here doesn't mean the kernel's actually there. The point is just to like recreate this like offset that exists. This 1 megabyte offset from whatever kind of base region. So for whatever reason, in physical memory, we like don't want to load the kernel like literally at 0. But yeah, like sure, why not leave some room below it? I can see that being a good thing, because if you're literally at the edge of memory, that's maybe just like asking to have bugs where you like literally just go off the end of memory. And so maybe give it some extra padding room and you can like catch that, I don't know, whatever. So give it some padding to be not right on the edge. And we kind of need to therefore recreate this padding zone later. So now I set this trivial page directory that maps from current base up a bunch to physical. Yeah. The key point is that it's this 4 megabyte region. Okay. Thanks for bearing with me through that. But now I have like much better understanding, yeah, of how this works. Grab a sip of water. Quickly check on the stream quality, make sure it's still okay. Okay, seems to be fine. Yeah. So maybe we can actually move on. Yep. Yeah, maybe I'll take a quick look at this actual page directory thing. So page directories. Yeah, so this is not the only thing we can look at. We also need the page tables. And it might also be a good time to get out my Intel manual. I don't know if I can find this fast enough. Okay, took a while to load. Trusty Intel manual. I would love to. It would be so cool if I could quickly find what paging looks like. 32-bit paging. Is that a diagram? I think this is what I want. I'm just gonna take this picture, put it into the picture area just for reference. Right. So this is what we're doing. Page directories. CR3 points to some page directories, which is a block of memory. What is it? Is there 512 entries in each one or something like that? I kind of forget. And then each of these is like this whole entry with a bunch of bits, and it points to a different part of memory with a page table. And then each of these entries here maps one 4K page. This is like OS 101. It's like operating systems from 1990 or something like that. It's yeah, okay. And crucially, this it's not totally clear from this diagram what these things are. So these two things are literally objects we need to create with our code somehow. It's like a real data structure. This thing is just physical memory. Yeah, so this thing points to a physical memory address, and then the offset gets added to get a final position. But this thing is not a data structure. This is just memory, but it looks exactly the same as the other two. And so really, in order to do this, in order to do simple paging on 32-bit x86, we need basically two things, which is exactly what we're seeing in the code. The page directories and the page table entries. Kind of curious what those look like. Maybe they are... Anyway, thank you for the subscribe. I just heard the thing pop off. Mudasir Khan, thank you for the subscribe. Still getting used to this streaming thing. Yeah, and we're seeing this kind of unusual syntax where we have this array. I think it's 512. Let me see if I'm right. No, 1024. Okay. Maybe it's 512 on 64-bit. but I actually kind of forget what the structure. Maybe it's only 30. It's probably 32-bit entries. Is there an easier? Hmm. 32-bit. Okay, maybe that doesn't really matter. I was pretty sure the page table entries are 64-bit. It's been kind of a minute since I have looked at any of this stuff, but I'm not going to get too bogged down right now. 4 megabyte pages. Oh, this is kind of a key picture to record that for later. Yeah, 32-bit entries. Right. Okay. Anyway, all these entries, we only need so for first one to map interesting. So it's two entries that map two regions to the same lowest 4 megabytes of physical memory. That wasn't immediately obvious to me so far. And so we can even illustrate this. So far, this is actually all physical memory is what I've been diagramming so far. Now we're going to take our first step into virtual memory, which I will make like yellow. So now we have our virtual memory, and maybe I'll actually put this on the other side here. So we have a 4 megabyte region. Hello. Can I not? Okay. 4 megabyte region down here. And like what? Oh, 20-second break. Be right back. Okay. The low 4 megabyte region, and we also have this like current base other, like technically it's 4 megabyte region, but we can only map 4K at a time. Oh wait a sec. But actually, yeah, that's not totally obvious to me. Oh, wait, that's in the page tables. Okay. Yeah, yeah, I think I should just read this comment. Like, I was kind of wondering, yeah, there's going to be multiple page table entries. Like, one page table entry can only map 4K. 4 megabytes is bigger than 4K. So there's going to be a lot of page table entries to do that mapping, which is a little bit... This is literally just like 1,000 entries. Oh my gosh, I didn't even see this. Wow, I was like, how could that possibly be? Wow, so interesting. So this thing is just like a forward declaration, so it can be referenced here, but then the actual like definition of the page table is here. And I will just take the time to really understand this, I guess. I think it's that important. Okay, yeah, but I was kind of little bit confused by there's only one page table. Right? There's like, no, there's one page table with like I think it's literally, is it literally 1,000 entries? It's literally 1,000 entries. Okay, that makes sense. Is it literally 1,000 lines in this file? Okay. Nice. But let me finish my picture. So this is virtual memory. And this is physical memory. This is also physical memory. Zoomed in to the top region. Okay. So we have our we have like our 4, there's like some region here, and then there's like this like kernel base, kind of like high memory kind of situation happening. And I don't really know where I should, like, it probably says it. Like, how much memory can you map with one page directory? It's probably not that hard to think about, because if one page directory has 1024 entries and each entry can map 4K, that would mean times 4. Wait a second, no, yeah. So 1024 entries times 4K divided by what, 1 megabyte? 4 megabytes, okay. So that's kind of like all coming together for me. I'm finally kind of getting this now. So because like this whole like 4 megabyte range is used in all these different places here. And I think it's like what they literally say it here. I just didn't read it. 4 megabytes is a very convenient amount because you can map that amount with one page. So one page table, and therefore one page table, one page directory entry. This interesting. We also map. Yeah, that's kind of also what confused me, because maybe let me finish my diagram, because we're actually mapping 2 regions. And so like there's like this like 4 megabyte range. So actually, time to draw some more bad lines. So this thing, maybe I'll make the color different to make it a little bit easier to read. So we got this thing. And then we have this thing, right? I don't know if this diagram makes any sense. I don't know if I'm doing it like in a way that's visually, maybe I should just have one single arrow. Yeah, I think I'm overdoing it. Okay. One arrow. Why can I not move this? Okay. So this thing is going to point down here. And also this thing points to the same place. That's like the key concept here. We have this one set of like page tables or whatever. that basically creates this. And I think there's one thing I will also point out is there's nothing here. It's like all empty. Maybe like a black rectangle is a better way to illustrate that. As far as this initial page table like thing we're doing is concerned, we have a completely like hollowed out virtual memory space. And remember, this is not to scale. We have 4 gigabytes of it's like not even this. It's like there's this thing, but then also like most of this is not even used either. Like I cannot stress how much this is not to scale. Or like we have like this completely empty address space except for these 2 4 megabyte strips, which both map to this same 4 megabyte region where like we have this padding zone. Maybe I'll just padding zone. Why did that come out? All caps. Padding zone. Padding zone. Yeah, I won't even include that. Padding zone, and then the kernel or whatever for like the rest. I don't know how far it goes. It's 2 strips mapped to that. And it would seem like this is not necessary though, because the kernel, like the whole, like the reason we're doing this is because our kernel is like compiled or whatever to be like run super high in memory. And as soon as we like jump into the kernel, we're like running here. So like, what is the point of this? And the answer, as literally the comment says, a few critical instructions in entry.s. The answer is, I believe it's just like this stuff. I believe when it's talking about these few critical instructions, it is talking about precisely these like 6 instructions, because these are the instructions that execute after we do the very dramatic action of enabling paging. Basically the code before the relocated label. Oh, is that right? Okay, so is it just these 2? Maybe. Interesting. I think you're right. I think I was wrong because, I mean, it also, again, literally says it in the comment. Why is this okay? We know the answer. Like, I know the answer to that now. It's because this thing sets up this map, which allows us to still safely be accessing super low memory addresses, even though like there needs to be like a huge comment saying like, warning, virtual memory on after this point, basically, because like it's very understated in the code, but this is like a super massive transition, and you need to be super careful about what addresses you use after you do this instruction, which enables paging. So now daily run, as you pointed out, it's like, okay, now the paging example, we're still running at a low EIP. Low EIP meaning like near the bottom of memory in the first megabyte. Jump up above kern base before entering the C code. So move relocated into EX and a relative jump into EAX. I actually don't get this. Move relocated into EAX and then jump there. Oh, but interesting. So relocated is a symbol in the kernel, which is linked to have these super high addresses. We can maybe even find the symbol here. Yeah, we can look at the symbol table of the kernel and see relocated, which is this super high. I mean, it's in our like kern base high zone or whatever. And the reason why I was kind of like confused at this, because if you were just reading this code, it's like, okay, like let's go from the top to the bottom. It would seem that this move relocated into EAX, so move this address and then jump there, which is literally just pointing to right here. So it would literally seem like it doesn't do anything, but obviously it does something because that's like it's here. And now that we know about this whole virtual memory thing, the really like super sneaky subtle thing that happens in these three instructions is if we go back to our like handy visualization of stuff. So like in this part of the entry.s, we are running in like very low physical memory, like running, you know, in here. That's what our code is. There's no virtual memory, and our code sets up the virtual memory, the very basic one, and enables it. And then with this instruction, just like with a snap of your finger, the world immediately changes from like this to like this is all you can see now. There's nothing else. And our code still, like, I think EIP literally still points very low here. Like everything, you know, everything is kind of assuming all, like, you know, EIP points really low here. Who knows what else points pretty low here. And so if we did not have this special mapping, then we would just like immediately like segfault, I think. I actually kind of would be curious to try that. Because it's like, yeah, like your code's like running, you do this very dramatic thing, you snap your fingers, you're in this new world now, and you better make sure you put some stuff there for yourself to land. Otherwise, you will just like, I don't know, like segfault, or I don't know, I actually don't know. Maybe we can try to figure it out, like page fault exception. Interesting. But are you sure about that? Are you sure you don't mean general protection faults? I believe what's going to happen is that EIP is going to try to do a memory fetch. Nothing is mapped. I mean, maybe you're right. Maybe it is, but page fault. Well, yeah, I mean, it's going to be one of those faults, basically. And then you look at the reason. I think it's general protection fault, though. Really quick, how would I figure that out? Interrupt and exception handling. Exceptions. Exception and interrupt reference. Man, what the? Where are you, GP? Double fault? Did I miss it? Stack fault? General protection fault, yeah. This is like getting into like the really like kind of details of like x86 and stuff like that, but I want to say like, is there just a list of all these things? I think I missed it. It doesn't matter that much. But what I kind of want to do is just try it. Now that we have some understanding of what's happening here, what would happen if we literally commented out this line? Oh my gosh, it reformatted the whole thing. I did not want to do that. Okay, stop. Wow. Oh, stop. Okay, jeez. I need to like format on save. That's annoying. I have my Clang format enabled or whatever. Okay. It just auto formatted 1,000 lines of page table entries. Okay, word. Okay. By the way, Daily Run, if you want to join the Discord, I would love to have you there. It'd be super cool. Just a couple of us. It's very chill. There's a link in some of my other videos, I think. And actually, I'll just take a moment to post the link here while I have people watching. Yeah, we have a Discord. It's pretty casual. It's pretty small. There's only one channel, and I just like use it to chat about stuff. So I will post the link in the YouTube chat right here. Yeah, we'd love for you to join us in there if you feel like it. No pressure. Anyway, so now we commented out this like seemingly useless but actually critical page directory entry. And does it build? Just out of curiosity, I'm going to like introduce a compile like error just to make sure. I'll add an X. Does it fail to build? Yes, okay, good. So let's say we don't have that anymore. I expect this to fail in an interesting way that I'm not quite sure of. Okay. Well, yeah, it's definitely failing, and it seems like it's just restarting like over and over and over again. Quit. I would be interested in running this in GDB. Is that possible? Oh, it would be pretty cool if we could do this and then like step through what happens. One of the other like big benefits of starting off with one of these existing systems is that they have a lot of this base infrastructure in place already for doing the build, but also debugging. But I'll be right back. Okay, nice. Last time, 20 seconds ago, I was just crashing the kernel, and I wanted to debug it, and GNU makefile, GDB, and this thing is super cool. So I need to add my, or was it GCC prefix or whatever? How do you do variables here again? What about now? Does this work? Oh. Okay, yeah. What about now? Okay, I'm kind of confused. Oh, I think I know. Then maybe I run QEMU. Is there a QEMU debug? Yeah, QEMU debug. Debug? What? QEMU GDB. GD. Is this even doing what I think it does? Yeah. Then I run this in the second pane. And now, wait, let me. So now I run that, now I run this, and now we are debugging the kernel. And I actually think this is I kind of like this is actually the first lab. I think the first lab is I think I've accidentally just done the first lab of the MIT class or whatever. Like we've spent this whole like 2 hours like trying to understand the physical address space and whatever, and I probably could have just like read this and not had like gotten my answers a lot faster. But I think this is just the first lab. So the first lab is like, okay, here's how this thing works. Here's how the memory layout works. And here's the debugging stuff. So let's take a look. Let's, I want to get to, I don't know, this is like the bootloader or whatever. Can I set a breakpoint on something such as entry? That's pretty cool. I think that actually worked. So can I continue? Okay, that did not work because the breakpoint didn't get hit. Once more. Step. This is gonna, wait, this is gonna be not, this is gonna be very ineffective. I cannot be single stepping every single instruction, can I? Well, I mean, I can obviously, but there's a lot of instructions involved here. I need a faster way. Like, I'm not going to be stepping through every single instruction of reading the segments. Although this is kind of interesting. It's like that relative jump. Where else in the code is there like a indirect jump like this to EAX? Did I accidentally like get there already? No? Yeah, I have no idea what where I am. Yeah, there's no symbols or like anything. I wonder if I could just directly do my read elf. Right. No, I wanted the read elf. Yeah. Can I just do this? Can I break on this address? What? If I continue, what happens? It doesn't hit it for some reason. And this thing just entry. Am I doing that right? Entry, current, entry.s. That's like this file, right? Right? But xi. Oh, I can't access the memory now. Wow. What? My comment triggered a build warning. Okay, I'm gonna delete my comment, or maybe I'll just remove the word warning, or maybe the pound define warning thing. So now I just want to just for fun like. Oh, okay. Wait a second. Yeah, that doesn't work. So I was trying to disassemble at this like entry address thing, which I thought would reveal this instruction. but it didn't. I think that's just zeros or something like that. Okay, I don't know. Something, yeah, that did not like work exactly like I wanted. It's kind of, yeah, it's kind of frustrating that I can't just like, I have to hold down enter here and watch us go through like a million instructions to like, yeah, if I just hold down enter long enough, what happens? Will this take like years to get to the crash? But maybe I have a feeling maybe I made a mistake. So, I mean, this is just a point. One thing that's kind of interesting, all of these addresses so far are below the 1 megabyte line, which I now know is 1 with 5 zeros after it. And yeah. I don't know. I don't know what code is running right now. Well, 5:53 on my time. Almost time to end the stream. Even though I didn't really write any code today, I feel like it was a pretty good stream. Though I feel like I learned a lot, and have a way better grasp of the fundamentals. Okay, yeah, I'm gonna give up on that. But I am excited to at least see that, you know, we were able to like understand this at a pretty fundamental level and even understand it well enough to like, you know, do a fake bug experiment or whatever. So that feels good. I'm going to remove the bug. So, and now we should be able to do our normal thing. Good. So now we fixed it. Yes, and I mean now like I have very deep understanding of how this works. I feel like I have like pretty strong understanding. And just to finish, yeah, this like explanation of this whole thing. So what happens? Yeah, so that's very interesting. So you're like running code right here. You do this instruction to enable paging. The world changes on an instant. We have cleverly prepared our landing with our page tables. And so now we have this first entry that continues to map this low region. So everything continues to work. So we are executing like right here in this low region. And we don't want to do that. We want to transition to actually running the kernel where it was compiled and like designed to be ran, which is way up here. And so we want to get out of here. And this is actually so interesting. Like we find the address of the relocated symbol, which is way up here, as we were just seeing in the symbol table. It's like this high number because the kernel is linked and designed to be this high in memory. And we load it into EAX and do a relative jump. And so we like seamlessly jump from down here to up here in virtual memory. But it's like there's like identical copies of the program and the code. There's identical copies of these instructions in both places. Like there's also a copy of this instruction down here. But we just seamlessly go from like move and jump right here. And then that instruction takes us all the way up to this move all the way up here. But there's also a copy of this, like all this other pre-init code that will never run up here. This code will only ever run down here, I believe. Yeah. So that is, yeah, there's no real copy. I mean, yeah, there's no, when I say copy, that's a good point. The data exists once in physical memory. It's just a mapping. And it's just, yeah. There's one copy of the data. It's mapped twice, but so there's like a two virtual copies of the data, basically. And you seamlessly go from one and transition directly into the other one with this line. And then, yeah, as Daily Run was saying, then once we're up here, we nuke the frame pointer. Yeah, I mean, the frame pointer, I mean, actually, that's one question. I don't know what stack this is running on. Because the kernel does not set up a stack. So the bootloader, it's running on the bootloader's stack. Okay. That is interesting. The bootloader is running, and then it just directly calls into the kernel. Without changing anything about the stack. So technically, this first entry point of the kernel still runs on the bootloader's last stack frame, which is kind of interesting. I wish I could like break here, because then we would be able to see that like these local variables are kind of like visible still in the stack frame, I believe. So it runs on the bootloader stack, and then we need to nuke it because now we're like way up high. So I don't know where the bootloader stack is. Yeah, no idea. But now we're trying to kind of reset things and get going for our own kernels, like proper like C runtime and its new life, like living up here, basically. And the way we do that is we nuke the frame pointer. It says for debugging reasons. We set the stack pointer. Breakpoint to the physical address of entry next time. Oh, good point. I mean, let's do that right now before I have to leave. So we're running this and run GDB and entry. You mean here? I mean, didn't I kind of, I thought I kind of tried that. Wait a sec. The physical address is this. Wait, I thought I tried this. So this is the physical address, right? Right? Isn't that like that is the physical address of entry. It has, so it's one, there's so many. Yeah, right. There's 4 zeros and then a C. No, you said 3? Are you sure it's 3 zeros? Oh, okay, wait, so you're totally right. Okay. I could have sworn I did that previously. But yeah, I mean, so now, I mean, thanks a lot. Yeah, now this is totally working. I wonder if my experiment like messed things up somehow. Like, let me just quit this. Or maybe I need to do this again. So maybe the address changed after I recompiled it. No, it didn't. Okay. Break. Right, continue. Okay, okay. I don't know why that didn't work last time, but now we're right in the entry, which is super cool. And we are, literally this instruction is about to enable paging. Cannot access, error while running stop hook. Cannot access memory. Okay, so we are beginning to observe like failure of operation because we didn't map the lowest virtual memory page anymore. We have nowhere to land after we've just done that transition. We're trying to like access the next instruction, which is not even mapped. So now that starts to fail. And like, I don't know how to, like what happens now. So now we have entered one of the like signal handle, or no, it's not, like interrupt handlers probably. And I don't know, we're in some like interrupt handling segment that was probably set up by the bootloader, maybe. No, it's not. It's going to be boot.s. Maybe not. I actually don't know what I'm talking about. There's like some code that's running here. Maybe I can grep for EAX again. I don't see that instruction. Yeah, right. That was kind of my intuition too, daily run, about some faults, like triple fault or whatever. But it looks like the code is continuing to run or something. Oh wait, maybe I understand now. So now we're running code, but what actually happened is that the processor like virtually like rebooted itself. And so now we're back at the start of the bootloader, maybe. So if I step, cannot access memory. Yeah, I don't really know. 20-second break. But yeah, I'm gonna end the stream pretty soon anyway. Yeah, so I don't really know what just happened there, but it is suspicious that we are just continuing to safely execute code, which which suggests that actually everything like in that moment, the like virtual CPU like QEMU like triple faulted or whatever under the hood and triggered a reset. We don't see this here. We don't even see it here. But then this is the hint, like you just said, Daily Run. Like this line appearing suggests that, okay, like we are completely starting from scratch again. Kind of like, you know, what happens right here, basically. So now we're just like completely back at the beginning, although it is a little bit weird because this like in our actual first boot, this long jump was there's a CLI option to tell him to print the interrupts. Maybe I will ask ChatGPT about that quickly. QEMU flag to print interrupts. That would be cool. I would like to see that. dash D, it says dash D int. Okay, so we need to, okay. So now I need to go, and this will be the last thing I do for today. QEMU dint. I don't know if this will work. That's just what I got from ChatGPT in 1 second. Okay, so now we're going to do a break of this thing. Wow, what the? Continue, step. Okay, I don't know if that was right or wrong, or yeah. I thought I did this right, so I put the dash D int thing there. We just triple faulted or whatever, and I did not see anything anywhere. So I don't know. Yeah. Anyway, I'm going to end the stream here. Thanks a lot for joining. This was a lot of fun. I learned a ton about numbers today. For example, that hex F is bigger than hex 4, and learned a lot about actually how this initial boot stuff works. And that's always been a goal of mine. So I'm going to end the stream here. Thanks a lot for joining. Join the Discord if you want. Like and subscribe and whatever. I'll see you next Sunday. All right, bye.